We're going to continue a discussion on the inverse circular functions. Just a quick refresher. We talked about the sine in a previous video, the sine and the inverse sine. We talked about the idea that in order to have an inverse, your function must be 1-to-1. Now the sine in and of itself is not 1-to-1, but we were able to restrict the domain, restrict it down from all real numbers down to just the interval from negative pi over 2 to pi over 2. And that gave us one, from a minimum to a maximum that incorporated all of the range values from negative 1 to 1. And so then we could use that 1-to-1 portion to create the inverse sine. And so you can see here the solid blue line was the sine after it was restricted, and then the dashed line here, or dashed curve, is the inverse sine. Okay, so that's all kind of review, just kept it up there. And then the other thing I wanted to point out is that the domain and the range switch. Okay, so the restricted domain becomes the range of the inverse sine, and then the range of the sine becomes the domain of the inverse sine, okay, or arc sine. Okay, now we're going to use all that information to work with the cosine. Just sort of not this specific information, but the ideas behind it, okay? So the cosine, if you want to consider, we know that the cosine of x is also not 1-to-1 because it's basically the same shaped graph as the sine, just shifted. And so what we need is a 1-to-1 portion of that graph. Okay, now just a real quick sketch of the cosine. It starts up at 1, goes down to -1 and back up. This would be at pi, and then over here is 2 pi where it gets back to the top. Okay, so that's just one wavelength of the cosine. A nice 1-to-1 portion of that is going to be from 0 to pi, that interval there, because all you're going to have is you're starting at 1 and it goes down to -1. And if you just consider that one portion as half a wavelength, it covers the entire range, but it restricts the domain so that it becomes 1-to-1. That's the interval we're going to use. We're not going to use the same interval as we did with the sine from negative pi over 2 to pi over 2, because that, if you extend this back to negative pi over 2 and to pi over 2, that interval does not have a 1-to-1 function, or I should say this way, the cosine is not 1-to-1 on that interval. Okay, so we're not going to use that, we're going to use the interval from 0 to pi instead. We could use the interval from negative pi to 0, that would be 1-to-1, but it's just not as convenient because we're more familiar with the angles from 0 to pi or 0 to 180. Okay, so that being said, on my graph here, I'm going to try to overlay both the cosine and the inverse cosine together with a few details in there so that you can see them. One thing I did put on my axes here, I put in blue all of the integer values, tick marks, and in red I put the radians, the pi's, right? I've got pi over 2 and pi. Pi over 2 is just over 1.5, and pi is 3.14 roughly. Okay, so it's like 1.57, 3.14, rounded off. So I have those approximately placed in here as well. So when we do the cosine, the regular cosine, we're going to restrict the domain down from 0 to pi. That way we have our 1-to-1 portion. The range, of course, is going to be -1 to 1. We still need that range. That way it covers all the values. So it starts up at 1, goes down to the x-axis at pi over 2, and then at pi it's down to -1. Okay, so that would be our cosine with the restricted domain. All right. Now, when I change that up, when I write the inverse cosine or arc cosine, its domain is going to be from -1 to 1. So we're going to be looking at an interval here from -1 to 1 in the x direction, and then its range is going to be from 0 to pi. Okay, so from -1 to 1, and then from 0 to pi vertically, all right? So what we're going to end up doing is interchanging some of these points. Actually, what I want to do is color coordinate a little bit. We're going to go with green for that one. So rewrite that. So y equals the inverse cosine. The domain is going to be -1 to 1. And the range, looks like my green marker's dying on me here. It's fading fast. Okay, there we go. And so I want to take this point at 0, 1, interchange the coordinates to get the inverse. It would be at 1, 0, which is the y-intercept or x-intercept. This point at pi over 2, 0 will become 0, pi over 2 when you interchange the points, the ordered pair. So that would be up here on the y-axis. And then this point at pi, -1, if you interchange pi and -1, you get -1, pi. So it'd be back 1 up to pi. And you'll see these 3 points will get a curve between them that's similar shaped to the cosine, just a reflection. And remember, the reflection needs to be across the line y equals x, which is a 45-degree angle or slope of 1. Okay, so if I were to plot the reflection, one thing that's interesting about functions and their inverses is that if they intersect, they will intersect on the line y equal x. So I can tell that the graph will go out to the right there and back to the left there. Okay, so the green graph now is the graph of the inverse cosine. It contains 3 important points. The left endpoint is -1, pi. The midpoint here, which is the the y-intercept, is at 0, pi over 2. And then this right endpoint is at 1, 0. Okay. Again, those ordered pairs, those 3 ordered pairs are inverted from the blue graph of the cosine. Now, one other thing that I should point out is that the range from 0 to pi happens to include angles from the first quadrant and second quadrant, right? This is 0 to 180 degrees. And so you end up with outputs from the cosine always in the first and second quadrants. Okay, so outputs are in quadrants 1 and 2. Okay, so they're always going to be in quadrants 1 and 2. It may be the case that you don't want an angle in quadrants 1 and 2. You may want an angle in quadrant 3 or 4. In which case you would have to use the quadrants given to you as an output, whether it be from your calculator or whether you're calculating these by hand. You will want to take the quadrants that you get as an output, or the angle you get as an output, and convert them to a similar angle in the third or fourth quadrant. Okay, so if you were to get, for instance, if you were to get an output from the inverse cosine of, let's say, 160 degrees, but you don't want a 160 degree angle, you want one in the third quadrant instead of the second quadrant, well, that's 20 degrees up from 180, so what you'd really be looking for is the similar angle in the third quadrant, which is 20 degrees down, which would be a 200 degree angle. Okay, so you make those conversions as needed with the outputs that are given. Okay. The next thing I want to do is I want to get into the inverse tangent and all the other inverse trig functions. I'm going to make the discussion a little bit briefer. Briefer, is that a word? More brief? I don't know. And yeah, so let's get rid of some of this. Okay, I'll leave those up there for right now. With the inverse tangent, we know that the tangent has vertical asymptotes, right, at both pi over 2, negative pi over 2 and pi over 2. So if we look at the graph of the tangent of x, there's a vertical asymptote at pi over 2 and another one at negative pi over 2. And the graph does have an intercept at the origin, goes down to the left and up to the right. So this is something familiar we've seen in previous videos. So this is the graph of the tangent roughly. And what's going to happen when you do this is 1 to 1. Now, if you were to continue the tangent, several wavelengths, every multiple of pi over 2, you get another vertical asymptote. So pi at 3 pi over 2 at 2 pi and so forth. And then you get this pattern repeating. Well, we don't want all of those wavelengths because then the graph is not 1 to 1. So we need this to be 1 to 1. And it's convenient to just use this one wavelength between the two vertical asymptotes. Now, when you convert this, I should probably list out the domain and range here. So we're going to restrict the domain just like we did with the sine. It's going to be negative pi over 2 to pi over 2. But this time the range is all real numbers because the tangent is not restricted to the interval negative 1 to 1. This graph goes down to negative infinity and up to infinity. Okay, so that's our range. Now when I draw in the inverse tangent, what we're going to end up with is we're going to be switching the domain and the range, right? So the domain becomes all real numbers, and the range is the interval from negative pi over 2 to pi over 2. What's interesting is when you reflect across the line y equals x, like we saw before, the vertical asymptotes will become horizontal asymptotes. And so you end up with asymptotes here at pi over 2 and at negative pi over 2. And then the graph is going to again intersect at the origin, and it's going to be a reflection of the red graph. Okay, so this blue graph that I just drew is going to be your inverse tangent graph. Okay. What's nice about the inverse tangent is you can plug anything into it. Okay, unlike the inverse cosine and the inverse sine, where everything you plug in has to be between negative 1 and 1, with the inverse tangent, you can plug anything into it. But again, your outputs for the inverse tangent are going to be in quadrants 4 and 1, just like they were with the inverse sine. This time, just like with the inverse sine, the quadrant 4 angles are going to be negative angles, and the quadrant 1 are going to be positive. Okay? So again, here the outputs are in quadrants 1 and 4. So be aware of that. You'll always get quadrants 1 and 4 out of the inverse tangent, okay? But you may need an angle in quadrants 2 or 3 depending upon the problem or the situation. So you may have to do a conversion like we talked about with the cosine, okay? Okay, now let's go ahead and take a look at the inverse cotangent. We'll do the cotangent next. Let's get rid of some of this. So the inverse cotangent, well, the cotangent itself does have two vertical asymptotes, but they're at 0 and pi. And you'll remember, if you'll remember, every multiple of pi gets, you know what, I said something wrong about the tangent. The vertical asymptotes are not at multiples of pi over 2, they're odd multiples of pi over 2. I just noticed I said that wrong. Well, anyway, maybe you caught that when I spoke it a few minutes ago. But the vertical asymptotes on the tangent would be at negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. They don't hit the integer multiples. Sorry about that. Just remembered I said that wrong. But anyway, with the cotangent, they're at integer multiples of pi. So 0, pi, 2 pi, 3 pi, and so forth. And so you get one right on the x-axis at 0, one over here at pi. I don't need any more because this will give me a one-to-one function. And then the cotangent is a decreasing graph. So right here in the middle, pi over 2 is an intercept. And it's going to look something like that. Okay, that's the cotangent. Of course, the domain we're going to restrict from 0 to pi, just like we did with the cosine. The range is going to be all real numbers. What am I doing here? All real number range. And then when we do the inverse cotangent, its domain is going to be all real numbers, and its range is going to be from 0 to pi. So again, what happens with the cotangent, just like the tangent, is that our vertical asymptotes become horizontal asymptotes. We'll have one on the x-axis, and we'll have one up at pi. And then the graph will have an intercept at pi over 2. And to make this a reflection across the line y equals x, if I drew in, or draw in the line y equals x, make that more dashed, then I've got to get the intersection here, just so I can see kind of which way the graph is going to curve. So it's not going to curve up, it's actually going to curve down to the right and up to the left from there. So it's going to go that way and that way. That's not too bad. Okay, so so the red graph there is the inverse cotangent. The nice thing here is that the outputs are in quadrants 1 and 2, just like the cosine was. Okay, so we don't have to worry about negative angles there. Okay, so that's the cotangent. Now let's look at the which one? Let's go with the cosecant and then the secant. So just draw these up very briefly, then we'll do a few examples in the next video. Or videos. Let's see. So if I do y equals cosecant of x. Now we know the cosecant is the reciprocal of the sine, right? So the sine, if I were to just sketch this in, I'll just make a dashed graph here just briefly. The sine goes up, comes down, goes back up, and then goes down on the left, up, and back down. That's not too bad. That's roughly the sine, right? Well, the cosecant is the reciprocal of that. So anywhere there's an x-intercept on the sine, you would have a vertical asymptote on the cosecant. So it'd be at pi, and at 2 pi, and at 0, and at negative pi, and at negative 2 pi. All right, and then the graph of the cosecant then is going to be in each of these sort of vertical strips, the reciprocal of the sine. So it's sort of a U shape going up, going down, here going down, and over here going up. Okay, so this is roughly the cosecant graph. Now the interval that we're going to choose, just a moment, let me check it here before I get too excited. For the cosecant, the interval we're going to choose is, well, we've got to find something 1 to 1. Each of these U shapes by themselves are not 1 to 1, right? They fail the horizontal line test. So we need to take part of one of those U shapes along with part of another one. We do need to cover the entire range. So we need to cover all the positive values and the negative values. So to restrict this down, we're going to take, with the inverse cosecant, we're going to work from negative pi over 2 over to pi over 2. The other option would be going from pi over 2 to pi, maybe, but it's nice to include 0, all the first quadrant. We like to include first quadrant angles when we can. So to do that, we're going to have to go left to get the other portion. So we're going to just be looking at that region there. So maybe I'll erase part of that. So the part that I'm drawing in green is the actual part of the cosecant that we're going to use. That's the restricted portion that we're going to use for this discussion. So the domain that we're going to restrict it to is negative pi over 2 to pi over 2. The range is going to be, now this is a bit difficult to write out. It's all these negative values from negative infinity up to negative 1. And it's all these positive values from 1 to infinity. So it's a combination of 2 intervals. Okay, so that's the range. Now, when we do the inverse cosecant, this one I'm just going to have to draw a separate graph. It's getting a little crowded there. Let's do this. All right, so if I do it in green for the cosecant, okay, so that's the portion of the cosecant that we'd be looking at. Then maybe in red we'll do the inverse cosecant. So if y equals the inverse cosecant, then we know the range. Oh, I'm sorry, did that backwards. The domain is going to run from negative infinity to negative 1, and from 1 to infinity, and the range would be from negative pi over 2 to pi over 2, okay? So, let's see. So we've got to figure this out. So it looks a little bit silly. Let's see. This graph from negative 1 down is going to go from negative 1 back in the x direction. The question is, does it intersect? Does it start here and go up, or does it start here? I'm not certain of that. Let's see, this is, okay, I can figure that out. So this is at negative pi over 2, right? So negative pi over 2, which is negative 1.5, roughly negative 1. If I want to switch those, it would be negative 1, comma negative 1.5. So it will be down, they will cross, and then go that way. And so that means this one, it's going to be up here, and it is going to cross and go that way. I don't know, something like that. It's kind of rough, but that works. Yeah. Okay, so anyway, that's the graph of the inverse cosecant, the red one. roughly speaking. Let's see, so this point up here at the right is going to be the point at 1 comma pi over, no, is that right? Yeah, 1 comma pi over 2. Yeah. Oh, I made a slight mistake here. I'll fix it in just a moment. This graph over, or this point over here is at negative 1 comma negative pi over 2. There is a mistake. There's a point not in our domain, or not in our range, and not. So 0 is an asymptote. You can't include that in the domain here. I don't know what I was thinking. So this domain is correct except for one point at 0. Technically, I should have 2 different intervals there. I wasn't thinking about that. I was going too fast. So, good thing I caught it though. I get a lot of comments on YouTube on that one. No, it's not true. I don't get any comments on YouTube. Don't forget to comment. I don't know. Okay. So, the domain here is actually going to be from negative pi over 2 to 0, and then from 0 to pi over 2. Oh. Okay, and so that's what's going to be our range. So it's still the same 2 quadrants, right? It's still the first quadrant and the fourth quadrant, but I just can't include that 0. Yeah, so that's going to be the range of the inverse cosecant. So there we go. Okay, so sorry about that little error there. I guess the next thing we'll do then is we're going to talk about the inverse secant. Okay, that's the last one we have to cover. My eraser. Let's see. So the inverse secant is going to look very similar to the inverse cosecant because its graph is similar with those bunch of U-shapes going with the vertical asymptotes. If I were to give you just a real quick sketch using the cosine, remember that the cosine starts up at 1, dips down, comes back up, down, and up. So there's a cosine, then you have your vertical asymptotes for the secant wherever there's a x-intercept for the cosine. So we'll do this quickly. And it's probably not a great scale, but that's okay. Okay, so there's my cosine graph. Now the secant graph is going to fit in here. Just like the cosecant with the sine. Okay, something like that. Now with the secant, we again need to restrict this down so that it's 1 to 1. We're going to use the interval from 0 to pi, that's pi, yep, 0 to pi, okay? And so I'm actually going to erase the portion we're going to use for this. That portion there, okay? So for the secant, these 2 sections then make it 1 to 1. And the corresponding domain is going to be from 0 to pi over 2 and then pi over 2 to pi. I won't make the same mistake I made with the cosecant. So it's the interval from 0 to pi over 2 and then from pi over 2 to pi. Again, it's from 0 to pi, but then we've got to pull out that pi over 2 because that's where the vertical asymptote runs. And then the range is going to be negative infinity to negative 1 and 1 to infinity to get that top portion. So when I sketch the graph of the inverse secant, Let's see. This is up at 1. Oh boy. Well, our where's this? So pi has got to be, that's 3 up. 1. I'm going to run out of space. I better redraw part of this just to give myself some space here. Well, maybe I won't even fit it on this graph. I know that when I switch this around, my maximum is going to be up at pi. And then my vertical asymptote here at pi over 2 becomes a horizontal asymptote at pi over 2. And then my graph starts at 1 in the x direction. That's my y-intercept becomes an x-intercept. And then it goes up to the vertical asymptote, which means here it would go over to the horizontal asymptote. And then here, my graph is at -1 up at pi, and then it would go down to the horizontal asymptote, okay? Well, not down. This one goes down, that one goes back, I guess. Okay, so correspondingly. Okay, so this would be the graph of the inverse secant, and again, the domain of this one is going to be the range from the prior. 1 to infinity. Hopefully that matches up. And then the range is the prior domain. Okay, so that should work. Again, here the range is going to be all angles in the first and second quadrants, just not including the 90 degree or the pi over 2 angle. Okay, and just like all of the other functions, if your output is not in the desired quadrant, so if you want an angle in a third or fourth quadrant for this one, you're going to have to convert those angles over to a corresponding angle in those quadrants.